welcome to this video. In this video, we are going to study about the industrial manufacture of nitric 5 acid. Nitric 5 acid is manufactured industrially through a process referred to as the Ostwald process. Now, for Ostwald process to proceed, it has to, we require the raw materials for the process, and we require the conditions that will favor the same process. So the raw materials for the Ostwald process, we have three. We have ammonia, water, and air. So we have ammonia, water, and finally air. And now we move to the conditions. The conditions that will favor the Ostwald process are as follows. The first one, we have a temperature. We have a temperature of 900 degrees Celsius. The second one, we have a pressure of 9 atmospheres. And finally, this process requires a catalyst. That is, for our case, we are going to use a platinum rhodium catalyst. So here, it requires a pressure of 9 atmospheres. And finally, a catalyst. For our case, we are going to use platinum rhodium catalyst. After the conditions, we move to the steps of the Ostwald process. The first step is the purifiers. In the purifier, the mixture of ammonia and air is purified, that is to remove impurities. For example, dust particles and other gases. Now, the reason as to why we have to remove impurities is to avoid poisoning the catalyst that is used in this process. After the purifier, the mixture of air and ammonia is pumped to the compressor, where the air is then compressed to a pressure of 9 atmospheres, that is to reduce the volume of the two gases. After the compressor, the mixture is then pumped to the heat exchanger, where it is preheated. It is preheated to a temperature of 230 degrees Celsius. After preheating it, it is then pumped to the catalytic chamber, where the two gases, that is ammonia and air, react over the platinum rhodium catalyst at a temperature. Here, the temperature is raised to 900 degrees Celsius. So here, after raising the temperature to 900 degrees Celsius, the mixture of ammonia and air will then react over the platinum rhodium catalyst, whereby ammonia is oxidized to nitrogen, to oxide, and water. So the equation at the catalytic chamber will be ammonia with air. We get nitrogen 2 plus water, gas. Here we have liquid. Then you balance the equation. To balance this equation, we are going to put 4 here, another 4 here, then 5 and 6. So that equation has been balanced. After nitrogen 2 has been produced, it is then pumped back to the heat exchanger, where the air is cooled. That is, now nitrogen 2 gas is cooled at the heat exchanger, then pumped to the reaction chamber. In the reaction chamber, nitrogen 2 gas will then react with purified air for us to obtain nitrogen 4 oxide. For us to obtain nitrogen 4 oxide, we balance this one. It has been balanced. After obtaining this nitrogen 2, we have a conditions that will favor this nitrogen 2 oxide, which is the temperature should be below 45 degrees Celsius. That will favor production of nitrogen 4 oxide. After nitrogen 4 oxide has been produced, the gas is pumped to the final chamber, which is the absorption chamber. In the absorption chamber, The nitrogen 4 gas is then mixed with water, that is against the downflow of water, for us to obtain nitric 5 acid and nitric 3 acid. So the equation at the absorption chamber is nitrogen 4 with water. We will have nitric 5 acid plus nitric 3 acid. Sorry, aqueous, then is liquid, and then we balance this one. It is balanced. The nitric 3 acid that was produced is further oxidized by the excess air to nitric 5 acid. So the other equation for the absorption tower will be nitric 3 acid further oxidized by excess air for us to obtain nitric 5 acid. So to balance this one, we are going to put 2 here and a 2 there. So oxygen is 4, 6, it is balanced. This one is aqueous. Now, the nitric 5 acid produced through this process, that is the Ostwald process, is 65% concentrated, whereby it comprises of 65% nitric 5 acid and 35% water. Now, after that, you find that we are going to summarize the whole process with a flow chart, that is the Ostwald process flow chart, in this manner. So here we have the purifier. This one is air. We have ammonia. Gas. From the purifier, in the purifier I've said impurities are removed. For example, the dust particles through electrostatic precipitation, the water droplets through passing it over concentrated sulfuric 6 acid. After the purifier, we move to the next step, which is the compressor. Here, it is compressed to a pressure of 9 atmospheres. That is, this is purified ammonia and air. After the compressor, the compressed air is then pumped to the heat exchanger, where it is preheated. To 230 degrees Celsius, then pumped to the catalytic chamber. Now, from the catalytic chamber, here the temperature is 900 degrees Celsius, and it has a catalyst, which is the platinum rhodium catalyst. Now, the ammonia gas and air will be passed over the platinum rhodium catalyst, where they react to produce nitrogen 2 oxide. So here, the nitrogen 2 oxide gas produced is then pumped back to the heat exchanger. And the equation for the catalytic chamber, we will be having it in this manner. Ammonia with oxygen, we get nitrogen 2 plus water. So here we have 6, 4, then 5, here we have 4, gas, liquid. So this is the equation at the catalytic chamber. Now, nitrogen 2 oxide produced is bumped back to the heat exchanger. So here we have nitrogen 2 oxide. Then in the heat exchanger, the hot nitrogen 2 oxide, this one is hot nitrogen 2 oxide, is cooled and finally pumped. So this one is the cool nitrogen 2 oxide. It is then pumped back, that is, it is pumped to the reaction chamber. In the reaction chamber, nitrogen 2 oxide gas is then reacted with purified air. The purified air will react with this one, that is nitrogen 2 oxide, to produce nitrogen 4. So the equation of the reaction chamber, we have it in this manner. We obtain nitrogen 4, which is a gas. Balance gas and a gas. After the reaction chamber, we move to the absorption chamber. This is the absorption chamber. Now here, into the absorption chamber, nitrogen 4 oxide is pumped to the absorption chamber, likewise to the unreacted nitrogen 2 oxide and air. So here we'll be having nitrogen 4 oxide plus air and unreacted nitrogen 2. So in the absorption chamber, nitrogen 4 is pumped against the downward flow of water, whereby nitrogen 4 will combine with water to produce nitric 5 acid and nitric 3 acid, whereas the unreacted nitrogen 2 oxide is pumped back to the compressor, whereby they will combine with the preceding air and ammonia. So here, nitrogen, this one unreacted nitrogen 2 is recycled back in this process, that is to minimize wastage. Now, the equation at the absorption chamber will be, we have nitrogen 4 gas plus water. We get nitric 5 acid plus nitric 3 acid. Then we balance this one that way. Now the nitric 3 acid produced in this chamber is further oxidized by this air, that is the excess air, to produce nitric 5 acid. So we have nitric 3 acid aqueous with excess air. We obtain nitric 5 acid. So here we put through there. This one is nitric. Yeah, it is that way. So this one is balanced. The equation that leads to production of nitric 5 acid is this one and this one. So here we have 65% nitric 5 acid. So the nitric 5 acid produced here is 65%. And you find that for us to obtain a more concentrated nitric 5 acid, in our case, we are going to distill this nitric 5 acid produced and passing it over concentrated sulfuric 6 acid that will remove the water that is present, that is 35% contains water. So the sulfuric 6 acid will remove the 35% water for us to obtain concentrated nitric 5 acid. And the nitric 5 acid produced in this process is a colorless liquid with a density. It has a density of 1.24 grams per cubic centimeters. Those are the two properties of the nitric 5 acid that is produced through the Ostwald process. Thank you for watching this video. In our next video, we are going to look at the Haber process. Like, share and subscribe to this video.